So this is part 2 of our chapter 3 lecture on instruction set architectures. And we're starting with section 3.2, the components of an ISA. So before we look at a real microprocessor in detail, we're going to talk about the 3 elements of an ISA. Its register set, its addressing modes, and its instruction formats. And together, these define the assembly language level programmer's view of the processor. So there's really 2 assembly language programmers, the human and the compiler. All right, so the human programmer, that's you, writes assembly language either, like in this case, a student in a class, studying computer architecture, or as a professional who's writing code to program a computer or is debugging a system at the assembly language level. So most low-level or machine code is produced automatically by a compiler that generates code from a high-level language. So to put this into context, right, you maybe have learned like C#. And so C# is translated down into what we call an intermediate language, which is then translated down into assembly language, which is then translated down to binary. And so all high-level programming languages work this way. Everything has to go through some kind of translation step by the compiler. So this is why programmers don't really need to learn assembly code unless you're working at this level. And the distinction between the human and the compiler is important in the design of computer instruction sets because it's probable that a human can write short fragments of code efficiently using an assembly language. We're going to get some practice doing that. We can see that in the text. Humans have ingenuity and can be inventive and creative, and humans can exploit a machine's instruction set and produce remarkably compact or efficient code. It is difficult to produce very large programs in this way. Moreover, assembly language written by one person using ingenious design features, I can't talk, are often impenetrable and unreadable by another human. So, and as you study software development, you've probably heard your instructors say, like, part of what makes good code good is that it is readable. That we can read each other's code, that it's maintainable. And so humans can write high-level language code much more efficiently, much more reliably than low-level code, and write it in a way that other humans can read it. And so that's why in today's world, most programmers write at a high-level language and leave the production of machine code to the compiler. So the compiler, in this scenario, right, creates machine code automatically from a high-level language. And their automatic methods of code translation are often poor at exploiting the features of a particular machine. So although a computer architect may construct an ingenious machine-level instruction, a compiler may never use it. And compilers cannot just exploit all of a processor's features. An architecture that is good for humans may not be good for compilers. And if we look back in the 1970s and 1980s when microprocessors were being developed, manufacturers created interesting and exotic machine-level instructions that were later found to be virtually useless when the output from compilers was examined. And so this observation is one of the driving forces behind this revolution of the 1980s. So we'll start with talking about registers. I know you're probably sick and tired of hearing me talk about registers, but when it comes down to components of an ISA, conceptually, the register is the mostly useless part of a computer. Right? It's not even necessary. It doesn't do any computing. And indeed, most of those microprocessors from like the 70s lacked on-chip registers. So they just used a group of memory locations as the register set. Now, registers, however, are necessary for the efficient performance of computers and the practical design of instruction sets, and to be able to write the kinds of applications that perform at the level that we expect of modern computers. So if you want to read the history lesson, I definitely encourage you to do so through the text, learning about general purpose versus special purpose type registers and old stuff like load and store computers that only had memory operations that, anyway. Really what we want to talk about are more modern architectures, right? So the IA32 architecture used by the 8086, I mean, that was groundbreaking, and we only got to where we are because we had that kind of architecture. But really we want to start with Intel developing the 86K processor, which came from the 8086. It was a 32-bit machine with 32-bit registers. And there was like this competition between Intel and Motorola. Motorola took some different approaches to register architecture than Intel, which used general purpose registers. And so we've gotten to this point where today the ARM processor that we're learning about has 32-bit registers. It's a 32-bit program counter, and its basic word length is 32 bits wide. Registers are usually the same width as the fundamental word of a computer, and they're usually the same as the processing power of the CPU. That's not a definite, it's a usual. And so some computers have dedicated registers, different functions. Some computers have entirely different general purpose types of registers, but what we're focusing on is the ARM. So the ARM has 16 general purpose registers, 0 through 15. The 0 through 13 are interchangeable. They all behave alike. 14 and 15 have additional functions. 14 is the link register that holds subroutine return addresses, and 15 is the program counter. And so although you're free to use R13 in any way you desire, good programming practice requires that R13 be reserved for use as a stack pointer. And so really we have 0 through 12. So are you sick of hearing about registers yet? They are important. I talk about them being useless, but essentially we would not be able to perform operations at the speed that we're performing them at without them. So one other important topic of registers is what happens to the extra bits. And we call this data extension. So sometimes registers need to hold data values smaller than their actual length. So let's say we have a 16-bit half word, but we have a 16-bit register, or I'm sorry, a 32-bit register. What happens to the extra bits? And so you can kind of see here in the figure how this gets represented. When we have these extra bits, it's kind of processor dependent, but some set the unused bits to 0. So we have our 16-bit half word in our 32-bit register. 16 bits contain the half word, the other 16 bits are set to 0. Some leave the unused bits unchanged, and then some extend the 16-bit word to 32 bits, which is extra odd. So now we're going to talk about addressing modes. So we know that instructions operate on data and that data has to be moved to wherever it is to be processed. And the ways in which data is specified is to be collectively called, right? How we decide that this is the piece of data that we want is called an addressing mode. So in principle, there are 3 fundamental different addressing modes. There are a great many variations, but we have literal, or sometimes called immediate, which is the actual value is part of the instruction. And this is the most simplest form. So we have the operand. It's part of the instruction itself. So let's think about, like, if we had P equals Q plus 5. So 5 is a literal operand because it forms part of the instruction. It isn't stored in a memory location or a register. And the literal addressing is that it's constant and it can't be changed during the execution of a program. The operation P equals Q plus 5 always adds 5 to Q. Now the value of Q might change, but the constant of 5 never changes. This addressing mode is sometimes called immediate addressing because the operand is immediately available. It doesn't have to be read from a register or from memory, and computers use literal addressing to set up constants that do not change during the execution of a program. We've seen how we can use the hash sign in front of our values for the ARM processor when we want to specify a literal operand. And so that's how we do that. That's literally what you're doing, is setting up that literal or immediate addressing. Next, we'll talk about direct addressing, which is also called absolute. And so this is the fundamental addressing mode of the stored program, right? Our von Neumann computer, where the instruction is read during its fetch phase and then executed in its execute phase. When the operands specified in the instruction are read from memory, then that's how we have it. Direct addressing is widely used by CISC computers, the Intel IA32, right? That's the Pentium computers, or the 86K varieties. So we see this quite a bit. This is very widely used. Now, one of the biggest differences between that IA32 or 86K variety processor and the ARM processor is that load and store computers like ARM do not implement direct addressing. All memory operands must either be specified as a literal or indirectly via a pointer in a register. And you will see this as you start writing some assembly of your own, that you either have to create a literal value or you have to point it to a register. You're not allowed to assign a value any other way. So the third addressing mode has a bunch of different names. Some people call it indirect addressing, register indirect addressing, pointer-based, index. So if any of these terms, this is what we're talking about. In this form of addressing, the instruction provides the address of the register containing the address of the operand. This is a little shell game. So obtaining an operand requires 3 accesses in this case. We have to read the instruction, we have to read the register containing the operand address, and then we finally get the actual operand. So the register containing the address of the operand is referred to as a pointer register, which is why we sometimes call this pointer-based addressing. And load and store computers like the ARM will use these addressing modes to access operands in memory. And so when you write your ARM code, and you'll see this where we do like the LDR and we specify like register 1, and then we point to register 2 to indicate that the contents of the memory location who's in register 2 should be moved to register 1. And in ARM, in Intel, in Freescale, all assemblers can write this. This is like one of the most widely used ways to be able to address. So, quick detour here about instruction types. I've pointed out there's no fundamental difference between registers and memory locations, right? Registers are memory locations that operate on the CPU, but fundamentally, they're not really that different. The practical difference lies in the relative speed of access and the number of bits used to specify a register or memory location. So in practice, that means that computer instructions, like in the era of 8-bit computers, were not able to implement long memory addresses, with a few exceptions, which meant that an instruction could provide only one memory address. So looking at our different instruction types here, we have our memory to type memory to memory operations where a source or destination operand is in memory and it cannot be supported. And consequently, microprocessors generally provide 3 instruction modes. And so we can have this memory to register where the source operand is in memory and the destination operand is in a register, right? And we've talked a little bit about that's kind of like what we were talking about with literal addressing. Register to memory, so the source operand is in the register and the destination operand is in memory. Or register to register where both operands are in registers. And we looked at that in part 1 when we were looking at some of the assembly code and we were doing adds and subtracts. Both operands were in registers when we were doing the adds and subtracts. We were taking 2 register values and adding them or subtracting them and putting that in another register. So we've practiced that already. So at the heart of an instruction set, the architecture of the computer instruction itself is the instruction format. An instruction specifies the next operation to be performed. And although we will later discover that some processors like the Itanium series, that's the IA64 series, have instruction sets that can specify multiple operations because we're always modifying, right? Moore's law. Processors they're getting better while we're talking about it. So, but for the purposes of this introduction, we're going to consider an instruction to be a word that specifies what action is to be performed together with any additional information, right? Our literals, our registers, and our addresses. So we don't want to overcomplicate things. So let's talk about opcodes and instructions. Instructions can be grouped or classified in several different ways. The most important single factor in the design of computer architecture is the number of operand addresses per instruction. So for example, an instruction set that's implemented, like add, R1, R2, R3, would be a 3-address machine. A computer that implemented add, R1, and R2 would be a 2-address machine. See, this is easy. So you can have 3, 2, 1, and 0 address machines, and instructions can also be grouped according to the nature of their operation. So for example, we can use data movement that copies data from one location to another, data processing that operates on data, and flow control that modifies the order in which instructions are executed. So we can categorize either based on the address mode or, like I said, that, how it's doing it. What is the nature of the operation? So here's that in a little better of an example from our figure in the book where we have 3 operands and an instruction, 2, 1, or 0. And look what happens when we just have 1 or 0 if you try to add, because you think about what happens if I just try to add one operand. So in this case, add P, adds P to an accumulator and puts the result in the ACC, where if you just say add, it's going to pop 2 items off the stack, add them together, and push the result. And so we can definitely kind of shorthand things if that's kind of the intended behavior. So let's look at this in a little greater detail and talk about 2-address machines. So our CISC, those are like the Pentium or the 86K. They have the 2-address instruction format. So clearly we can't do stuff like P equals Q plus R with 2 operands. You can execute Q to P plus Q because then you're only using 2, right? One operand appears twice, first as the source, then as the destination. Add P and Q performs this operation. So if you just say add P and Q, then it's going to take P and add it to Q and put it back into Q. So when we're working with these 2-address type machines, Typically, the operands are either 2 registers or 1 register in a memory location. And here's some examples of how that add instruction could be written. A 1 address machine just specifies 1 operand in the instruction. The second operand is a fixed register we call an accumulator that doesn't have to be specified. So, for example, the operation of the 1 address instruction and, so if you just say and P, means take our accumulator, add it to P, put it back in the accumulator. We use this notation of A to indicate the contents of an accumulator. And this is, it seems like fairly simple, right? And so we can see here this like fragment of 8-bit code. This would have been from like a first generation 8600 8-bit processor. Your instruction set would have looked like this. And 8-bit machines have 1 address architectures. And so as you can imagine, 8-bit code is very verbose because you have to load data into the accumulator, you have to process it, and then store it to avoid it being overwritten by the next data processing instruction. So 1 address machines are still widely used in embedded controllers. They're ultra low cost, low performance system. We see this in toys, right? Toys that need, just a little processing power. We still use these. They're just not used in the modern computers that you and I want to use to do our work, right? And then, of course, 0 address machines use instructions that don't have an address at all, which kind of blows your mind when you think about it. So a 0 address machine operates on data that's at the top of the stack, and a 0 address machine is normally referred to as a stack machine. So pure 0 address machines are not practical. We load and store instructions that are needed to read data from memory, and we put data in memory. Operations with 1 operand, so things like negate, clear, increment, decrement, act on the element that's at the top of the stack, whereas operations with 2 operands, so add, multiply, logical OR, pull the top 2 elements off the stack, perform the operation, and then push the result. This operation used to add an item to the stack is normally called a push, and the operation used to remove an element from the stack is called a pop. Maybe you've heard these expressions before because stacks are very common in computer science. And so, again, not practical, but definitely an architecture that exists. They can be made to handle like Boolean logic. So you can see this example here, kind of the push and pop and add and sub and multiply. Right, so if we take a look at this example here, we can handle the Boolean logic and express this. It just takes a lot more work, honestly. So this is why we say that they're not practical. Then the last one that I want to talk about is a 1.5 address machine. So this gets a little weird, but that Intel IA32 family and the Freescale family are frequently called 1.5 address machines because their instructions specify 2 operands, where 1 operand is an address in memory, right? And the other is a register. The register address is kind of ironically called a half address, right? It's kind of like a half word because there's only a handful of registers compared with gigabytes of memory space. And so we can look at this example here of 86K code that demonstrates the evaluation of an expression and compare that with the code on an accumulator-based machine. So that's kind of where that comes from, that half address. So we've looked at the basic structure of processors, the elements of an ISA. Now we can kind of turn our attention to our real microprocessor and really dig into ARM. And the architecture of ARM processors has developed over the years. There's now several classifications of ARM processors, with each class intended for a particular segment of the market. So we have like embedded microcontrollers and high performance computers. And we're really going to discuss like A-class devices, so the A8, A9, A15. And if you've not heard of ARM processors before, I honestly think look around your house at some of the things you have, like what phone do you have, what computer do you have, tablets and things. Go look at what processors they actually use. Familiarize yourself with the architecture of what you're using in your daily life. I honestly think it's very helpful. So let's just take a trip down ARM lane here for a second, because I realize that some of you probably, like maybe you're never really paying attention to the type of processor that you're using, or maybe you're only familiar with like Intel versus AMD, and that's as far as it gets. So what is ARM essentially, right? So ARM originally came from Acorn RSIC machine, right? And they built the BBC microcomputer, which was based on an 8-bit architecture and used extensively in like British high schools. And the company was founded in 1990 as Advanced RSIC Machines by Acorn Computer, Apple Computers, and VLSI Technology. And so you heard me say Apple, right? They were one of the, like very early adopters or funders, at least, of trying to get these new processors developed. So the second generation ARM devices were 32 bits. They were essentially like used in very limited applications. Unlike Intel and AMD and Freescale, ARM does not build chips. They license their core processors for use in systems on chips, right? We call those SoCs. And in microcontrollers. So we have like 8 or 10 billion ARM cores that have been built. There's like 5 billion of them that are probably going to grow every year. It's a technology licensed by semiconductor companies. So you see them being used by Intel, being used by Freescale, Texas Instruments, Philips, Fujitsu, Sony. You've probably got at least 3 of them in your house. So there's a little bit of more history of ARM and the ARM set architecture, if you want to read about that in the book, how things kind of developed from Apple's Mac to Atari to Amiga. I personally find that kind of stuff fascinating, but if you want to skip the history lesson, we will jump right into ARM register sets. So we've talked a little bit already about, the ARM registers, the general purpose 0 to 13. 14 stores our subroutine return address. 15 contains the program counter. It's register 13 technically is reserved for use by the programmer as a stack pointer, but that is not like an enforced. That is simply good programming manners and considered to be best practice. So these registers all require a 4-bit address, which saves 3 bits per instruction over RSIC processors with 32 register architectures, which is a 5-bit address. And this makes the ARM a little unusual for an RSIC processor because it has only 16 general purpose registers. And 16 registers, right, like I said, requires a 4-bit address. It saves 3 bits per instruction over RSIC processors that are usually using that 5-bit address. And this approach allows the ARM to have this richer instruction set than some other RSIC processors. And here we can see kind of this register set in the figure, give you a little visual, as well as that current processor status register, those flags, those condition codes, and those operating modes that sometimes we want to check and reference inside of our code. Now, fortunately for us, there has been remarkably little change in instruction set architecture between today's high-performance machines and first-generation microprocessors. The instructions implemented by the ARM are fairly the same as those on the Pentium or the 86K, and they can be grouped into several basic types. Although individual writers will categorize instruction sets in different ways, our textbook chooses some rather broad groupings of data movement, arithmetic, logical, shift, program control. Here you can see some typical ARM instructions, right? This maybe doesn't look all that exciting. we've learned at this point that our whatever instruction that we want to do has some kind of 3-letter shorthand, right? We call that the ARM mnemonic, and then gives us an idea of how we should use it syntactically, and then uses our reference language to kind of give us that shorthand as well. So let's talk about the ARM assembly language. All processors, doesn't matter what, all, I know I rarely speak in definites, have an assembly language that was crafted by the chip's designers, although third-party suppliers may well create different versions of the processor's assembly language, and you've already seen some fragments of our ARM assembly language that we did in part 1. We're going to start to talk about some of the features that enable you to write programs that will run in an ARM environment, and we can see here the ARM instructions are written in this form, right? This right here. So we have our label, our opcode, operands separated by commas, and comments, which are prefaced by a semicolon. So we can take a look at some code here and kind of see what this looks like. So a label, starting with this, like this case, our label is test 5. The label is a user-defined field. It can be used by other instructions to refer to that line. So as you saw in our previous example where we were moving and branching, the label gives us that marked line that we can jump to when we want to branch. So it doesn't matter that about spaces after the commas. You can put them all together. You can just write them, operand 1, operand 2. If you like to put spaces after your commas, that's fine. Any text following the semicolon is going to be a comment field, and it's going to be ignored by the assembler. So if you've taken a programming class, which I'm assuming you all have, you realize that comments are there to improve the readability of the program, that they're necessary, and that especially in this case where assembly is desperately hard to read, comments on every line are by far the accepted norm. So let's look at an example here of a fragment of ARM code, right? Supposing we wish to generate the sum of the cubes of numbers from 1 to 10, and we can use the multiply and accumulate instruction. So we can see, and each line is commented, so we can definitely understand what's happening. We are clearing out the total in R0. So we use the MOV, the move, to take register 0 and put a literal 0 in it so that we're sure that we've cleared it out, which is good practice. And then we are also using a move on our register 1 to put a literal number 10. Now we're creating a loop, and we want to start at 1 and we want to go to 10. And we're going to count down. We're going to start at 10 and we're going to go to 1. That's why we're starting at 10. Then we're going to square the number. So look at this mul. This is our multiply. So we're going to take R1 and R1, because we're squaring, multiply and put that into R2. You can see that this line has a label of next. We're also going to cube the number. So we can see that instruction here. We're going to use subs. Now sub is a subtraction. If you add the S to it, it's going to set that condition flag so that we can check. We're going to decrement the counter. So we're going to take R1 and we're going to subtract by 1 and put that back into R1. And then our next instruction says, branch back on count not 0. That's why we need this condition flag, because the condition flag is going to get set. We're going to be able to check that. And if it's not 0, we'll jump back up to next and we'll repeat these instructions until this no longer branches back, and that will end the for loop. Now, as this points out, this is syntactically correct and it implements the appropriate algorithm, but it's not a program you can run. If you go type this in somewhere, you're not going to be able to run it. It's going to give you errors. And that's because there are two different types of statements when we're writing assembly. We have executable instructions that are executed by the computer, and we have assembler directives that tell the assembler something about the environment. And if we haven't set that environment up, then we aren't going to be able to run anything. So here is what that looks like, the structure. When we begin with a program that's going to be executed on an ARM computer or a PC with an ARM cross-developed system, then we can see here in this fragment of code, this demonstrates the structure of a simple program and takes that code that we just walked through about the cubes, but puts it into a state that will actually run. And so we can see these add-in areas here in the red. An area assembler directive defines a section of code. So in this example, this section, we're calling it ARM test. It has the attributes of code and read-only. The assembler directive entry tells the assembler where to find the instruction that's supposed to be executed first. And then we have to put an end, which is the assembler directive that's mandatory, tells the assembler that this is the end of the program. It's done. There are no more instructions. And so if you were to put this into like an assembler, our book talks a lot about UVision, but in our case, we're actually just going to be using a different program. So you'll see that in Canvas when you look at our course that I find is a little more approachable. But you can see what this looks like in the assembler. We have all of our code, paying attention to our tabs. Usually we try to format this out in a very specific way so that it is readable. And after this assembly language program has been written, we can then use the assembler to assemble it and execute it. And generally what we want to do is look at the disassembly, which gives us the disassembled code, which is essentially the code generated by the assembler, but converted back into source form to show you both code and instructions. And so this also gives us our memory address information and allows us to see all of the different instruction steps. Now, I'm not going to get too in the weeds with the UVision program because we're not going to be using it for this class specifically. But generally, when you are using these types of programs, you do get like a registers window so that you can review all of the registers and see all the values inside. And so you'll want to make sure and look at that for our course so that you can get familiar with using the visual, it's called visual program that we'll be using to practice writing our assembly code. So this isn't by far a be-all, end-all list. You'll find lots of references. I've linked some in the course to demonstrate some assembly language directives, but here are some ones that are kind of important. So if we want to equate a name to a value, set up some constants and different sizes of memory. When we reach the end, like I said, end is mandatory. Entry, we need to set a starting point for execution. When you want to name a region of code or data, and then if you want to make sure that your instructions are correctly aligned within your 32-bit boundaries and you're not going to accidentally reach out into a section of code that your program maybe doesn't have access to or that you aren't writing values to, then you can also use align. So one of the things that kind of makes assembly programming so challenging is this idea of pseudo instructions. So as you're looking around online and you find some resources or you find some assembly code and you're like, hey, I want to try this out, and I type it into Visual and it doesn't run and it's telling me that isn't an instruction, this is what's happened. So a pseudo instruction is an operation that the programmer can use when they're writing the code, but that actual instruction doesn't exist. It's like a code name for a real instruction. The assembler knows this, if it's designed to know this, and generates the suitable code to carry out the same action. So here's an example. We can't write MOV register 0 with this address or literal value to load register 0 with a 32-bit value specified here because an instruction is only 32 bits long in total. So this pseudo instruction, ADR, which takes our destination label and loads 32-bit address of the line label to a register, is like a way that we could get around that. And you'll find a lot of these pseudo instructions, and probably the most egregious one that's used in the book is LDR. LDR something equals a value. The compiler will generate the code that allows the register to, or whatever value you're giving, to be loaded with the stated value, but LDR is not an assembler instruction. The assembler is going to use MOV or MVN if it can. So if you do something weird with LRD and then it's like, this isn't working, it's really because LRD is not an actual instruction. It's a pseudo instruction if you wish to use move instead. But as you're going through the book and you're typing things out, or you're going online and you're looking at resources, this is sometimes why you're like, this looks like an instruction, but it's not working. If the assembler that you're using, there are several types of assemblers, if it's not designed to use a pseudo instruction, it won't recognize it, or it might be designed to use it syntactically different than the resource that you're looking at, and then this is where the confusion comes in. So this is where I'm going to end Chapter 3, Part 2. Chapter 3 really starts to dig into a lot of how to write assembly, right? So like practical considerations and data processing instructions and how to write actual ARM-related assembly code. And so that's what we're going to focus on going forward. So not so much lecturing as looking how we can use assembly using our visual program and getting some practice using some of the things that we're reading about in Chapter 3.